Okay, it's time for us to talk about the 265 exam 2. Paper exams. I remember the good old days when we had paper exams. Yes, it was true, we risked those paper cuts, but there's always something nice about the tactile feel of a test. Well, hopefully someday in the future we'll get to go back. So we want to get into this test, so that means we need to really open it up. So let's start digging into it. Take a stapler so we can do some deconstruction. And let's begin. And let's see what this test has. We'll do our classic start at the beginning. Number 1. Sketch the domain for the function below and shade the interior of the region. Make sure to indicate whether a boundary is included a solid line or not included with a dashed line. Only need to provide the sketch. No other work will be graded. Okay, so now what do we see? Well, we see there's a couple of issues, right? What do we have? Well, we see that there's a fraction, so we can't divide by 0. That means that the denominator, this needs to be strictly greater than 0, because there's a square root here. So normally what's inside the square root, x plus y plus 1, has to be greater than or equal to 0, but we can't have it be equal to 0. Okay, so let's make our notes. So we need x plus y plus 1 to be greater than 0. Now, if you think about this as a line, usually we like to solve for y. That says y has to be greater than minus x minus 1. So there's an intercept here, has a slope of negative 1, and so we should draw, we're going to do a dashed line. This is our scratch work. The reason it's dashed is it's because it's a strict inequality. There's a log here. Now what do we know about logs? We know the inside of the logs has to be positive. So what's inside is x squared plus y squared. And we need that to be positive. And you're like, well, that's pretty easy, right? Because x squared is always greater than or equal to 0, and y squared is always greater than or equal to 0, so it's always positive, right? Wait, almost always. What about 0, 0? You're right. 0, 0 is a problem. Okay, so we're going to mark 0, 0. That's a bad point. Can't include it. By the way, we forgot to do something here. We drew the line, but we said, where should we shade? So y has to be above the line, so that says we want to shade this part right here. Just going to do some light shading now, because we're going to do more shading as we go on. All right, then we have the square roots, right? So we have 2 square roots. By the way, we don't care about this. Minus sign doesn't make any difference at all, so don't worry about that. It's just what's inside the square root. We need 4 minus x squared to be greater than or equal to 0. That's the same as saying x squared has to be less than or equal to 4. Now when does that happen? Well, we could say if I took the square root of both sides, that would become absolute value of x is at most 2. Or another way to think about that is that negative 2 is less than or equal to x is less than or equal to positive 2. So that says I'm in between. So here's negative 2, positive 2 for x. So I have to be in here. All right, what about this other one? Okay, similar process. 9 minus y squared has to be greater than or equal to 0, which says y squared has to be less than or equal to 9. Square root, absolute value of y less than or equal to 3, or negative 3 less than or equal to y less than or equal to positive 3. So what does that mean? Well, it says we got to stay in between positive 3 and negative 3. So we've got to stay in here. Now, we've done a lot of scratch work. Let's figure out, where do they all overlap? So there's really 3 shaded regions, right? It's got to be above this line. It's got to be between these 2. It's got to be between those 2. So that's this part right here. And we say, all right, we're going to include our edges. Remember, this edge is a dotted edge, but make sure we throw out 0, 0. So our final answer looks like this. We make sure we throw out 0, 0, and then we're going to come down here, and we come down to the point 2, negative 3, and then we're going to have a solid line all the way up to 3, and a solid line across to negative 2, and then a solid line down to 1, and the rest here is dashed. And finally we shade. And that's it. That's our domain. And there we go. Kind of an interesting picture, but that's the process, right? Whenever you have a domain question, you always say, where are the problems? And how do we avoid the problems? And if we avoid the problems, life is good. All right, well, that's number 1. Number 2, find and classify critical points of f of xy equals x to the 4th plus y to the 4th minus 4xy plus 1. Well, there's a giveaway word here, the word classify. So whenever you see the word classify, you know it's a very particular type of problem. That means that we're going to use our second partials test. So let's start with the find. Find always has to come first, so that's our step 1. So we look at our partial derivatives. F sub x, that's 4x cubed minus 4y. Got to set that equal to 0. And f sub y, well, that's 4y cubed minus 4x. Got to set that to 0. And we can clean that up. The first equation, divided through by 4, rearrange, tells us that y has to be the same as x cubed. The second equation says that x has to equal y cubed. Now, how do we solve? Well, we can do a substitution. For instance, I can take this y in the first equation, plug it into there. We get that x has to equal x cubed cubed. And here you would multiply the exponents together to get x to the 9th. So when does x equal x to the 9th? Well, you might say divide by x, but be careful. If you divide by x, you might lose the solution. We don't want to lose anything. We want to make sure we keep all the solutions. So better to group. So put the x across. X to the 9th minus x. Pull out an x. X to the 8th minus 1. Like, okay, how do you factor x to the 8th minus 1? Well, one way you could do it is you could think of x to the 8th. Really, this is like x to the 4th squared minus 1 squared. So it's x to the 4th minus 1, x to the 4th plus 1. Difference of squares. Okay, well, how about this x to the 4th minus 1? Same idea. It's x squared minus 1 times x squared plus 1 times x to the 4th plus 1. Well, how about this x squared minus 1? Well, that's x minus 1, x plus 1. And of course, you got the x squared plus 1 and the x to the 4th plus 1. Now, you can't have x to the 4th plus 1 be 0. Because if I raise something to the 4th power, it's greater than or equal to 0. Same thing with x squared plus 1. Which means our only possibilities for x are x equals 0, 1, or negative 1. So, now we know what x can be, so what about y? Well, y is x cubed. So our points are x equals 0, 0 cubed. X equals 1, 1 cubed. X equals negative 1, negative 1 cubed. Okay, those are our points. And of course, we've got to classify. So we've done the find. Now we're to step 2, classify. Now for that step, what we're going to do is look at this thing we call d. That's fxx, fyy minus fxy squared. So, what is fxx? Well, that is 12x squared. Fyy, 12y squared. Fxy, negative 4 squared. All right, so let's plug points in. Plug in 0, 0. What do we get? So plug in d, 0, 0. We're going to get 0 minus 16. Well, I don't really care about the value. I care about the sign. We saw the sign, and it opened up our eyes. We saw the sign. Well, what is this value? It's negative, and we know if this d is negative, that means that this corresponds to the kind of point that looks like this shape. In other words, this is a saddle. Okay, so 0, 0, that's a saddle. Okay, how about 1, 1? Well, what will that be? That'll be 12 times 12 minus 16. Now, what do we know? Well, they're big, but that doesn't matter. We just need to know positive or negative. And it's positive. Okay, what about this 12? Well, hold on. Wait a minute, what about this 12? Remember, positive, you have to go a little bit deeper. So if d is positive, it's a local min or max, then you run into what is fxx? It's either positive or it's negative. And in our case, fxx is positive. All right, so what does that mean? Well, if xxx is positive, then that means we are at something that looks like this. It's a local min. That's really the second derivative test, but that's a different story. All right, minus 1, again 12 times 12, minus 16, still positive, and lo and behold, fxx is still positive, and so this is also a local min. And there we go. That's our answer. That wasn't so bad. This is a fun test. I wish all our tests were this fun. Well, hold on. We still got some more problems. Let's see what happens next. Number 3. Suppose the temperature at xyz is given by this expression, 80 plus xy plus sine yz. In what direction, as the unit vector, should you move from the point 1 pi 1 to decrease the temperature as quickly as possible? Okay, and then there's a second question, which is also find the directional derivative in this direction. There's a key here, as quickly as possible. In fact, we want to decrease as quickly as possible. So that says we're looking for the direction of greatest decrease. Well, we've heard that sort of idea before, and we know that the direction of greatest decrease happens in a very particular way, and in particular, that corresponds with negative the gradient at our point P. So let's take our function. So here's our function t. We'll write it down again just for reference. So we have 80 plus xy plus sine of yz. The gradient of t, well, take our gradient. In the first slot, derivative with respect to x, well, there's only one x, so we get y. Second slot, derivative with respect to y, well, there's an x. Then here, we'll get chain rule, z cosine yz. Last slot, well, there's only one z, so we're going to get y cosine yz. Now, we plug in our point 1 pi 1. We get what? Well, in the first slot we get pi. In the second slot we get, well, 1 plus 1 times cosine of pi. Well, wait a second. Cosine of pi, we know what that is. That's negative 1. So this whole thing is 0. Well, that's rather convenient. And then in the last slot, what do we get? Well, we get pi times cosine of pi. But again, cosine of pi is negative 1. So we end up with pi, comma, 0, comma, negative pi. Okay, so this is the gradient. That's the direction of greatest increase. We want the greatest decrease. So the direction will correspond to negative pi, comma, 0, comma, minus pi, which of course we can put the negative in. Negative pi, comma, 0, comma, positive pi. Now, is that our answer? Well, remember they said unit vector. Okay, so let's take the magnitude of this. So the magnitude of negative pi, comma, 0, comma, pi would be the square root of pi squared plus 0 plus pi squared, which of course you can pull out the pi squared and you get pi root 2. So we take 1 over pi root 2 times this vector, and that's our unit vector that points in the right direction. And in fact, you can multiply that through. So we end up with minus 1 over root 2, comma 0, comma 1 over root 2. And there's our answer. Now that's for the first question. Also, okay, what's this also? Find the directional derivative in this direction. Well, it looks like we're going to have to do a lot of work, but actually that's a freebie. So the directional derivative is the rate of change in that direction. Now, we're decreasing, so it's going to be negative. What's the size? The answer is it's the magnitude of the gradient. So the directional derivative in the direction of greatest decrease is minus the magnitude of the gradient at that point. But from our work, we already know what this is going to be. So we get minus pi times root 2. And there's our answer for the directional derivative in that direction. All right, that's number 3. How are you doing so far? Did you do good? I hope you did. I hope you did. I hope you enjoyed these. Number 4. Find the tangent plane to the surface x squared plus z squared e to the power y minus x equals 13 at the point 2, 3, 3 divided by the square root of e. And give your answer in the form ax plus by plus cz equals d. Now, this is an expression of the form f of x, y, z equals a constant. Now when you see that, you say, okay, that's like we're finding a plane to a level surface. The way we find a plane to a level surface is we use the gradient. Wow, what a powerful tool that gradient is. It is a powerful tool, you're right. So, what do? You start by taking the gradient of capital F. So we take the derivative with respect to x. We get 2x, and don't forget there's also an x there, minus z squared e to the power y minus x, comma. Take the derivative with respect to y. There's only one y. So that's z squared e to the y minus x, comma. Take the derivative with respect to z. It only shows up right there. So that'll be 2z e to the power y minus x. Next, that's not a normal yet. That's a function. A normal should be numbers. We need to plug in our point. So, gradient of f at 2, 3 over root e. What happens? Well, 2 times x, 4. Z squared. Well, that's going to be 3 over root e squared. So, that's going to become minus 9 over e. And we're going to have e to the power y minus x, which is e to the 1, comma. Z squared, again, 9 over e. E to the power y minus x, which is e to the 1, which is e, comma. Then we're going to have 2z, so that's 6 divided by root e times e to the power 3 minus 2, which is e. Now we get some cancellation there and there. So if we simplify, we get minus 5, comma, 9, comma, 6 root e. Okay, so what is this? This is our normal. Now that's not our answer. In fact, it tells us what our answer needs to look like. But what that is this is our A, B, C. So we say, okay, so we know our answer looks like minus 5x plus 9y plus 6 root e times z equals something. So we need the something. How do we get the something? It needs to have this point, so we're going to plug that in. So minus 5 times 2 plus 9 times 3 plus 6 times square root of e times 3 over square root of e. Well, the square root of e's cancel. So that's what, minus 10 plus 27 and plus 18. Well, if you put those together, that would be a number. Well, no, it'd be 35. Come on. It's not that hard. Minus 10 plus 27 would be 17, and 17 and 18 make 35. So our answer, minus 5x plus 9y plus 6 root e times z equals 35. And there you go. That's it. Life is good. Life is wonderful. All right. Number 5. The equation x minus z equals arctangent yz implicitly defines z as a function of x and y. Ooh, implicit. So almost surely this is about implicit differentiation. In fact, we see find partial z partial x and partial z partial y and give the answer in the provided boxes. Now we know whenever we see something that involves implicit differentiation, whether we're taking a test or not, we're like, we're sitting there thinking, it's our little thought bubbles, and we say, all right, so what are we thinking? The key is to remember that when we have an implicit relationship, is we're going to think of z as depending on x and y in some form. So we just got to figure out, all right, what are the right derivatives? So we're going to take our derivatives. So let's take our derivative with respect to x. So this is our take derivative with respect to x notation. So the derivative of x with respect to x is 1. Derivative of z with respect to x, well, remember, z depends on x, y. See, that's what we're thinking. So it's something. So what is it? Well, if we don't have a better notation for it, which we don't, we just say the derivative of z with respect to x is the derivative of z with respect to x. Equals derivative of arctangent. Ah, arctangent, my old friend. It's good to see you. So the way you take derivative of arctangent is it's 1 over derivative of the inside. Sorry, 1 over 1 plus inside squared times the derivative of the inside. Now y, because we're taking derivative with respect to x, we're treating that as a constant. And z, of course, still depends on x. So we're going to have y partial z partial x. Now, at this stage, what happens? Well, we should move stuff around. So, for example, we can move this over to here, and we get that 1 is equal to, and when I move it, both terms have a partial z partial x. I'll go ahead and factor that out. Partial z partial x times y over 1 plus yz squared plus 1. So, dividing through, we get partial z partial x is equal to 1 over y over 1 plus yz squared plus 1. Now, I don't like fractions within fractions. I mean, who does? Who does? So let's multiply top and bottom by 1 plus this yz squared. And if we do that, that'll get rid of our fraction downstairs. So we'll get 1 plus yz squared, divide that by y plus 1 plus yz squared. And there's our answer. So that's partial z partial x, so let's put that in the box, right? Because we follow instructions. Because following instructions is a good way to make sure we get all the points. And our goal has got to get them all. All right, so there you go. Now, how about derivative with respect to y? All right, same process. Derivative of x with respect to y, 0. Oh, that's even better. So there's minus derivative of z with respect to y, because of course derivative of z with respect to y is derivative of z with respect to y. Because remember, that's what we're thinking about when we work on this. Equals the arctangent. Ah, arctangent. Every time I see the word arctangent, just my heart skips a beat. You know, it's just such a beautiful function. Now, how do you take the derivative of yz? Be careful. How many y's are there? There's 2, right? Because of how we're thinking about. They're multiplying together, so we've got to do the product rule. So we take the derivative of the first. Well, the derivative of y with respect to y is 1, so we get a z. Plus, then y times the derivative of the second, which is partial z partial y. Okay, so let's multiply that out. So that would be z over 1 plus yz quantity squared plus y over 1 plus yz squared times partial z partial y. Now we'll do the same thing we did before. We'll move that term across. We'll also move that term across. So rearrangement. So we get minus z, divide that by 1 plus yz squared is equal to, and now when I move this across, both terms have a partial z, partial y, so that can be factored out. Partial z, partial y over 1 plus yz squared plus 1. Divide. Partial z, partial y is equal to minus z over 1 plus yz squared. Divide that by y over 1 plus yz squared plus 1. Again, fractions within fractions, we don't like that. That's not why we signed up for calculus. We signed up for calculus for beauty. Let's clean it up. Let's make it beautiful. So, multiply by 1 plus yz squared over 1 plus yz squared. In the top, you'll get minus z. Downstairs, you'll get y plus 1 plus yz squared. And of course, put it in the box. So, negative z, divide that by y plus 1 plus yz squared. And there you go. That's number 5. Wow! We're flying! Woo! We could, take this test twice if we wanted to, with all the time we're going to have. Okay, number 6. Given that g of xy is a twice differentiable unknown function. Unknown means we're not going to give you a formula for it. Twice differentiable just says I can take derivatives 2 times. And we have a lot of information. G of 2, 4 is 2. G sub x of 2, 4 is negative 1. G sub y at 2, 4 is 1. Gxx at 2, 4 is 3. Gxy at 2, 4 is negative 2. Gyy at 2, 4 is 2. Then use all of this information. Look, they even italicized all of this information. It's like they really want to emphasize. Use everything. And what are we going to do with that? We're going to get an estimate for g of 2.2 and 3.9. Simplify your answer to a single number. Oh my gosh. I'm a little bit nervous about this last part. That means we might actually have to be careful with our algebra and our arithmetic. But you know what? Let's do it. Let's be careful. Let's figure this out. Now let's think about this. We have to use all the information. Well, what kind of thing uses all the information about the function, the first, and the second derivatives at a point? So this, the thing that uses all the information, is a Taylor polynomial. Aha! So, what does that say? Well, we're going to have, our point is at 2, 4, because that's where all our information is at. So, we have near the point 2, 4, which is, that's okay, that's where we're near. We can say that our function g of xy is approximately, and oh boy, I hope I have space. I'll write small here. You plug in the function at 2, 4 plus the derivative with respect to x at 2, 4 times x minus 2 plus the derivative with respect to y at 2, 4 times y minus 4. Now, if we were to stop there, that would be our linear approximation, which is an approximation and is useful for estimates, but it doesn't use all of the information. So we keep forging ahead. Plus gxx at 2, 4. And now we're going to multiply this by x minus 2 squared over 2. Plus gxy at 2, 4. Multiply that by x minus 2, y minus 4. And then finally, plus gyy at 2, 4 times y minus 4 squared over 2. All right, we fit it in. Good. Now, that uses all of the information. So, let's just make sure we get our numbers right. G at 2, 4 is 2. Gx at 2, 4 is minus 1. So, 2 minus x minus 2. Gy is positive 1 plus y minus 4. Gxx is 3. And there's an over 2, so I'll write this as 3 over 2 times x minus 2 squared. gxy is negative 2. So minus 2, x minus 2, y minus 4, and gyy is positive 2. So that's 2 and an over 2, so plus y minus 4 squared. All right, so that's for any xy. Now we're going to use that xy. So g of 2.2 comma 3.9 is approximately 2. Now 2.2 minus 2 is 0.2. 3.9 minus 4. Well, 3.9 is smaller than 4, so it's actually negative 0.1. Plus, then we have 3 halves times 2.2 minus 2 is still 0.2 squared. Then we have minus 2 times 0.2 times negative 0.1. That's our 2.2 minus 2, 3.9 minus 4, and then plus minus 0.1 squared. Okay, so 2 minus 0.2 minus 0.1. So let's see what happens here. 0.2 squared. Well, don't worry about the 0.2. Think about just 2. 2 squared is 4, but now you got that 0.2, right? So that means you have to move the decimal place over, and you do it twice. So really, that's going to become 3 halves times 0.04. Minus minus makes this a plus. And now, what do we have? Well, 2 times 2 times 1 is 4, but again, it's going to become 0.04. And then here, we're going to have a 0.01. The minus goes away because of the square. 0.1 times 0.1 is 0.01. Let's clean this up. 2 goes into 4, so that leaves us 0.02 times 3. So that point is really 0.06. Here is 0.04. If you put these together, you get 0.1. But notice here we have a minus 0.1, so we can actually cancel those off. So we get 2 minus 0.2 plus 0.01. Well, that's 2 minus 0.2 is 1.8. And if you add a 0.01, 1.81. And that's it. That's the answer. That's a single number, and that's a good estimate. Is it a great estimate? Yeah, it's okay. I mean, we don't know. It's unknown if it's a good estimate because we don't even know what the function is, let alone how good the estimate is. But we definitely used as much information as possible, and it's a very reasonable estimate. In other words, it's the best that we could do given the information that we've been given. All right, that leaves us with one more problem. You know, these tests always go by so quickly. It just feels like we started this just a few minutes ago. Oh well, I'm sure we'll get more chances. So what do we have? We have f is a function of u, v, w, u is a function of x and y, and v is a function of x and y, and w is a function of x and y. Write down expressions for partial f, partial x, and partial f, partial y by using the chain rule in terms of appropriate partial derivatives of the functions f, u, v, w. You know, I suspect that this problem might have something to do with the chain rule. Now, if you're wondering why I think that, my main clue was the fact that it says the chain rule. It's a pretty big clue. So we know this. We have our function f. It depends on 3 variables, u, v, w. And each one of those depends on variables x and y. So this is sort of our tree of variables. So if I want to find partial f, partial x, in other words, how is the function changing as I change x? Well, how do I get from f down to x? And the answer is I have to go 3 ways. So, in each step, there's a partial derivative. So, partial f, partial u, partial x. So, partial f, partial u, partial x. Now, partial f, partial v, partial x. This part is actually not so bad. It's just you got to be patient. Make sure you account for everything. Then here, finally, partial f, partial w, partial x. All right, good. So that's the one for partial f partial x. How about partial f partial y? Well, it's going to be the same thing. In fact, the only change that happens is wherever there was a y, we put, sorry, wherever there was an x, we put a y. So that's partial f partial u, partial y, partial f, partial v, partial y, partial f, partial w, partial y. And there you go. Okay, so that's part A. All right, let's look at part B. Now I'm going to leave part A kind of visible because there's kind of something that happens where when you're working on a problem with multiple parts, part B oftentimes has something to do with part A. I am suspicious that that might be the case here. So let's check that out. So find f sub x at 1, 0, f sub y at 1, 0 for f of x, y equals e to the power uvw, u equals 3 log x plus y, v equals x minus arctangent y, and w equals x plus y. Oh my gosh, another arctangent? Oh man, this is like a really good test. I like that. Okay, now one thing we could do, and it wouldn't get full credit, but it'd be a lot of work, is to say, okay, let's put in 3 log x plus y for u, and x minus arctangent y for v, and x plus y for w. That would do a lot of work. And one of our goals is to say, let's get to the point where we don't have to do a lot of work. In fact, that's a golden math. How can we simplify this to something which is easier for us to do? So let's use what we have up here. So let's talk about what we know. First off, we know x is 1 and y is 0. So we're thinking this is x, y, 1, 0. Let's talk about u. Yes, I'm asking you. No, I mean this u. So 3 natural log of 1 plus 0 becomes 0. How about v? You get 1 minus arctangent of 0, which is 1. How about w? 1 plus 0 is 1. All right, so far so good. Okay, so there's our x, y, there's our u, v, w. Let's find these partial derivatives up here. So what is partial f partial u? Well, taking the derivative of this with respect to u, that would be vw, and then it would be e to the u vw. Now, when we plug this in, what does this become? Partial f partial u, well remember, u is 0, v is 1, w is 1, so it's 1 times e to the 0, which makes this 1. How about partial f partial v? Well, that would be uw e to the uvw, which is 0 times 1 times e to the 0. That's going to be 0. How about partial f partial w? Well, that would be u v e to the uvw, which is 0 times 1 times 1, which is still 0. All right, well, let's go with our other terms. Partial u partial x, that's 3 over x. Plug in x equals 1, 3. Partial u partial y, 1. Partial v partial x, 1. Oh, these are really simple. Partial v partial y, well, derivative of arctangent is minus 1 over 1 plus y squared. We plug in y equals 0. This is negative 1. Partial w partial x is 1, and partial w partial y is 1. So now we have all the values. So we just follow the rules. So partial f partial x would be partial f partial u is 1, partial u partial x is 3, plus partial f partial v is 0, partial v partial x, 1, and partial f partial w is 0, partial w partial x is 1, which makes that 3, And partial f partial y would be, well, again, partial f partial u, that's 1. Then partial u partial y, 1, plus 0, because this is still the same partial f partial v, and then partial v partial y, -1. Ooh, that might change anything. Haha, it doesn't because of 0. It's really hard to overcome 0. 0 is very, very challenging to overcome, which is why you never want to get that 0. And then finally, partial w partial y is 1, which gives us 1. And that is our answer to our last problem. Ah, we're already done? Oh well, even the good times have to come to an end. So that was our exam 2. Well, we'll get one more exam, right? And it should be a good one. So, all right, well, thanks for being so patient. Hope you did well on the exam. And if you didn't, well, you still have a chance to do a little bit better. And make sure you're taking care of yourself. We love you. Keep in good health, keep in good spirits, and we'll talk to you later. Bye.